All right, welcome to this episode of Takehome X3 Key. I'm just going to run through the solution to these problems and hope that they help you understand OChem a little bit better. All right, problem number 1. This doesn't work. Why not? What we're trying to do here is carry out a Wolff-Kishner in the presence of strong base, hydroxide, and heat. It does not successfully reduce the carbonyl. What happens? Well, there's a couple of things that can happen, and one of the couple of things is what a few of you thought might happen, which was that since this is the product of an aldol reaction, it's entirely reasonable that the elimination could take place, in which case what you get is the conjugated carbonyl, and that's certainly not what you want, and that could go ahead and get reduced down to that alkene. Again, not the product you want. What I actually think, and that's full credit right there, but what I actually think probably happens is more likely that the base attacks in a retro sense to give you the retroaldol that decomposes the molecule to give you the original enolate and the aldehyde. Either way, you're sunk, and that simply doesn't work. All right, problem number 2. Fill in the missing information. Well, we've got an epoxide, and we're going to go from the epoxide to this alcohol, where this whole big chunk of carbon has been added. And that chunk of carbon looks like this. So if this is the bit that's been added, and it's clearly adding to here, and we know that is an electrophile, then this chunk of carbon must be added as a nucleophile. So the easy way to make this into a nucleophile is to make the Grignard or organolithium. So you got two choices: make it an organolithium reagent, make it a Grignard. Either one will work just fine. What next? Well, this, then, well, not that. This then is oxidized up to the ketone. And I'm just going to abbreviate this AR for the aromatic ring. So what can be used to oxidize this? Well, not just any oxidant, because what I got to worry about here is that I have a vulnerable alkene. So I don't want to add anything that will react with my alkene. So if I were to add something like chromic acid, which is dissolved in water, that's bad news because the strong acid would protonate my alkene. And if I were to add KMNO4, that's bad news because then I would oxidize my alkene to the diol. So really the only choice here was to add PCC, which is relatively mild and has no strong acid present, no water. So that's your choice for B. C then goes ahead and takes that ketone and it's converted to this alcohol. And here's our aromatic group. So again, knowing that this is an electrophile means I must add that group as a nucleophile. So yet again, I need to add this 3-carbon piece with, either the Grignard or the organolithium. And then that that would be 1, and then 2 would be an acidic workup to give me that alcohol. Now I have to erase and put my aryl group back in, because now I have to see what's happening here with my Grubbs reagent. So what I have is, let's change this to something bright. 1, that's not very bright. 2, 3, 4, 5, 6, 7, 8, 9. What I know about Grubbs is that these two are going to be chopped off, and I'm going to make my new alkene right here between those two. So that would be a 7-membered ring. So the bottom line here is my final product is the product of alkene metathesis with the Grubbs reagent. So here is my 5-membered ring. And so 1, 2, 3, 4, 5. So I need to make that into a 7-membered ring. 1, 2, 3, 4, 5, 6, 7. 3, 4. Nope, that's not 5, 6, 7. Try again. If at first you don't succeed, there we go. So that should be a 7-membered ring, and my alkene is right there. So I also have my alcohol here. That's my final product. So that is problem number 2. And I'm going to make these really incredibly short so that you can watch the mini lectures that you want to watch and not have to watch all of them. But I hope that you will find these helpful.